One of the major arguments against ID is that it does not make any empirically testable predictions, and hence is not science. Rather, it is claimed, various hypotheses to explain the apparent design of the cosmos and life are merely metaphysical. And so this is one of the, among scientists, claim is that the distinguishment feature between science and metaphysics or philosophy is the ability to make testable predictions. I don't necessarily agree with that, but I think if you could show that ID made testable predictions, that would go a long ways in establishing it in science. So in this talk, I will present two examples showing how robust testable predictions can be drawn from fine-tuning related hypotheses, design, multiple universe, and assumptions underlying the fine-tuning argument. This shows we must be very careful in too quickly making the separation between what counts as a scientific hypothesis and what merely counts as a metaphysical hypothesis. So to begin this whole thing, let me briefly review the fine-tuning argument, just to get your bearings. Here's the argument in its briefest form, as I could give it to you. This is from, the first overhead is from a student many years ago when I started exploring it in class, and she put that on her exam. And the fine-tuning argument, you can think of each constant of physics, let's say the strength of gravity. There's a number that determines the strength of gravity that's plugged into the physical laws. Or the strength of the strong nuclear force that holds protons and neutrons together in a nucleus. Or the cosmological constant that determines the expansion rate of empty space. Each of those could be thought of as dials in one analogy here. And unless if they're perfectly set, life can't exist. If they're not perfectly set, just within one part in 10,000 billion, for example, then life cannot exist. So then the argument is there's two ways of explaining this. One is everything is set perfectly right for life. That seems, in many people's mind, to indicate there must be a designer behind everything. After all, that would be way too unlikely under the chance hypothesis. Then there's another hypothesis that many people put forward, and that's what I call the mini-universe scenario. And there exists some physical process that generates a very large, if not infinite, number of universes. Every time a universe is generated, the parameters of physics are set at random. Because of the large number of universes generated, eventually one will turn up with just the right values, the parameters of physics, for life to occur. And this is a cartoon image. No one actually thinks there's a little machine out there. But this is my cartoon image of what's going on. So that's the conveyor belt generating universes. This is taken very seriously among certain segments of the physics community, as I found out in a talk I delivered at Stanford last year at a symposium. So certain segments, I say. And then the most common scenario for that that's offered today is based in inflationary cosmology. And it's that the universes are generated out of this pre-space, which is like an ocean full of ivory detergent, and bubbles form out. So the universes are little bubble universes. And then I argue against that. Even if there is such a universe generator, it only kicks the problem of design up one level, because if you actually look at the physical details, the universe generator has to be put together just right for life to occur. So that's the basic fine-tuning argument. And what we saw is one response is design, one response is mini-universes. Another key response is going to be important for what I discussed today. It's what's called I call the atheistic single universe hypothesis. That simply says that's the way it is and claims the fine-tuning argument that the universe needs an explanation is misguided in some way. Either you can't really speak of probability and improbability in this context, or there's no way of inferring from either design or mini-universes. So those are the three basic responses to this evidence from fine-tuning. Now, another analogy, which is going to be important for what we're going to do in drawing testable consequences, I'm going to give you another analogy here, and that's what I call the dartboard analogy. So this I want you to really fix in your mind, and here I've given you my website for if you want further information on the fine-tuning argument. I have various articles up there. I've written quite a few articles, as the program says, on this topic. So here's the dartboard analogy. You think of the range as possible values for these constants, let's say the strength of gravity, as this dartboard. And then there's a bullseye on the dartboard, and the bullseye is the range discovered by physics of the life-permitting values. And then in that analogy, you see the dartboard having hit the bullseye, and having hit the bullseye, you say, well, if the bullseye is really, really teeny, somebody must have aimed it. And so that's another analogy that works to give you design. Now, so keep that in your mind, and now we're going to switch to a thought experiment. So that was just background. Here's our dartboard thought experiment. And so we're going to see the relevance. Just move into the thought experiments. Don't worry about the relevance right now, because you'll see the relevance in a minute. So here's the dartboard thought experiment. Consider the following thought experiment. Suppose there is a 10-foot-long dartboard with a bullseye on it. Further, suppose that you have bad eyesight and can thus only see the right half of the bullseye. Finally, suppose you see a dart hit within the bullseye, so you know you're on the right-hand side, the dart hits within the bullseye, as this diagram has it here. It hits within the bullseye. That's within a few hundredths of an inch of the lower edge of the bullseye, but the upper edge is unknown. This seems very surprising to you. Of all the places the dart could have landed, why did it hit so close to the edge? And then your mind begins to turn over and you start developing several hypotheses. So you don't see what's going on. All you're looking at is the dartboard. It's all blackness behind you. You don't know whether there's a dart thrower throwing it or it's chance or what it is. So you have, actually it should be 4 hypotheses suggest themselves to you. Oops. Let me get that up there where you can see it. Okay. It happened by chance plus large bullseye. It happened by chance. The dart was just thrown by chance. No one aimed it. Plus small bullseye. Dart was aimed by an expert dart thrower plus relatively large bullseye, several feet long. So there's a huge bullseye, and dart was aimed by an expert dart thrower towards the bullseye. Dart was aimed by expert dart thrower plus very small bullseye, a few hundredths of an inch. So there's your hypotheses. And now, let's look at what you can do with those hypotheses. Well, I say clearly, hypotheses 1 and 2 do not take away our surprise. Remember, 1 and 2 were the chance hypotheses, small bullseye, large bullseye. So if it's just by chance, that's not going to explain why it hit so close to the edge. So we're still going to be surprised it hit so close to the edge, whether or not the bullseye is small or large. Neither does hypothesis 3, at least not under the generic dart thrower hypothesis, in which we assume that the dart thrower has no special desire to hit very near the edge of the bullseye. So if you thought there was a large bullseye and you thought there was an expert dart thrower throwing it towards the bullseye, and it comes right near the edge, it wouldn't explain why it was so close to the edge, because if an expert dart thrower was thrown, there'd be no reason to hit right close to the edge versus anywhere else in the bullseye. Only hypothesis 4, dart thrower plus small bullseye, explains why the dart hit so close to the edge. If an expert dart thrower aimed it, we would expect it to hit the bullseye. And if the bullseye is very small, say a few hundredths of an inch, then we would expect the dart to fall within a few hundredths of an inch of the edge. Okay, so now we're going to draw predictive consequences from this, and then I'm going to do a direct correspondence out of certain cases in the fine-tuning. So here's the next stage, is to draw predictive consequences. Now suppose we all along believed in the generic dart thrower hypothesis, And further, suppose we saw the dart fall very close to the lower edge of the bullseye, say a few thousandth of an inch. Wouldn't that give us very good reason to believe that the bullseye was very small, on the order of a few thousandth of an inch? Indeed, this would be the only hypothesis of those above, as I reiterated before, that would take away the surprise of it falling so close. Without this hypothesis, it would seem very coincidental for it to fall so close. In other words, we would predict that if we put on better glasses, the upper edge of the bullseye would be a few thousandth of an inch away from the lower edge. To see this more clearly, if that's not quite convincing enough to you, just imagine this happens like 10 times in a row. You see 10 darts come in, and 10 times in a row it lands within a hundredth of an inch from the edge. Surely, if you believe that the dart was being thrown by an expert dart player and that she had no special desire to hit near edges, you would conclude that the bullseye was very small. Thus, you would predict that the upper edge of the bullseye would be only a few hundredths of an inch above the lower edge, a prediction you would test by getting your glasses. Okay, so now you have a definite prediction about what you would see on the bullseye, and you can't see the dart thrower. So we can already begin to see what the analogy I'm going to draw is. The dartboard is what we can see with the laws of physics, what's testable. Whether there's a dart thrower out there, that we can't access directly with physics, okay? But we're going to see that we can, by thinking there's a dart thrower out there, we can actually get testable predictions out of it, as we have here. So let's move over then to the case of the fine-tuning. So let's apply this line of reasoning to the case of the fine-tuning of the weak force. And there are several other examples along the same line. And here's the example of the weak force. I claim, and we only have well-developed physical arguments to believe that a 30-fold decrease in the weak force strength would severely inhibit, if not eliminate, the possibility of life. But we have little direct evidence that an increase in the weak force strength would inhibit the existence of life. Thus, we only know the lower edge of the life-permitting region. Now, I'm aware some people claim that increases of the weak force and things like that, there's various claims out there, would inhibit life. I've carefully gone through a lot of the major fine-tuning arguments, and it's printed in this book if anybody's interested, God and Design. You can also get the reference from my website on my Vita. A lot of the arguments are not based on very sound physical reasoning, as I elaborate in the appendix. So I think it's still unknown in the case of the weak force whether a major increase in it would eliminate the existence of life. What we do know is that a small decrease would not. So it's right near the edge, and I don't have that figure available. So we know that a small decrease, we know the lower bound, just like we know in the case of the dart here. If that were the weak force, we know this lower bound. We know it hits very close to the edge, but we don't know the upper bound. And I think that's the case with several other constants. Now, if one assumes the total theoretically possible range of values for the weak force, it's a certain strength of a force. There's 4 forces in nature: strong force, gravity, electromagnetic force, and the weak force. That's the 4th one. So you have this range of values for the force, gravity being the weakest, and it's usually there was a standard measure for it. And then the strongest being the force that holds protons and neutrons together, which is considered 10 to the 40th times as strong, or 10,000 billion times as strong as gravity. So there's a huge range of force strengths. If you take that as the range of possible values for force strengths, the length of the dartboard here, okay, if you do that, then it turns out that the distance the constant falls from the lower edge of the life-permitting region is about 1/billionth of the theoretically possible range. And thus it seems very surprising for it to land so close to the edge. And if we represented the theoretically possible range by a foot-long dartboard, the dart representing the weak force constant Is there a problem?
Sorry, I just want to adjust your
Put it on now.
There we go.
The dart representing the weak force constant would have fallen 1/billionth of a foot from the lower edge of the bullseye representing the life-permitting region. Okay, so there's our physical example. And then again, just like in the other dart thrower case, we have 4 hypotheses to explain it. And I'm excluding right now the many-universes hypothesis, but if you want to include, there's a way of including it, but it simplifies things to exclude it. So atheistic single-universe hypothesis, what I explained before, that just the universe is a brute fact, plus large life-permitting region, so that's one hypothesis you come up with. Atheistic single-universe hypothesis plus very small life-permitting region, that's another one you come up with. Then you have design hypothesis plus large life-permitting region, and design hypothesis plus very small life-permitting region. That is 1 or 2 orders of magnitude of the distance, should be of the distance d, the constant is from the edge. So if it's a billionth of an inch, it should be within 10 to 100 billionths of an inch away from the edge. Order of magnitude is a power of 10. So it should be within, not too much, if d is the distances from the edge, it should be within a factor of 10 or 100 of d. Only hypothesis 4 explains why the constant falls so near the edge. And then I mentioned here I'm simplifying things by excluding the many-universes hypothesis. If you include it, you would have to go design plus many-universes. Okay, and these 2 hypotheses. Okay, and here's now we're getting to our result. Thus, as in the case of the dartboard analogy above, the generic design hypothesis, generic means the designer has no particular preference for edges of life-permitting regions, predicts that if a constant is within d of the edge of the life-permitting region, the other edge should be within 1 or 2 orders of magnitude of d of the first edge. For example, representing, like I did before, the theoretically possible range of force strengths by a 1-foot dartboard, we would expect with high probability that the upper edge of the life-permitting range for the weak force constant is within 1 billionth to 1/10 millionth of a foot of the lower edge. This is an empirically verifiable prediction. On the other hand, the atheistic single-universe hypothesis does not predict anything in this regard because it doesn't explain why it's near the edge. It doesn't explain anything. It just says it's by chance. So if you buy into the fine-tuning argument that you really have a legitimate argument going on here, and you need to infer to design, or if you buy into many-universes, then you actually get a predictive consequence out in these cases. You should have certain expectations with regard in these cases of where you only know 1/2 of the life-permitting region where the other half is going to fall. So in the case of the weak force, the predictive consequence is this. As we do further research on it, we should find that the weak force strength, if it's within a 30-fold decrease is the life-permitting into the life-permitting region here, we should predict that as we do further research, an increase in the weak force by 30-fold or something around that is going to be the upper edge of the life-permitting region. So we actually have a consequence we can drive. That's the important thing here. Now, so we could go out and test this. Now what I want to do is look at a little more detail, just it's slightly more technical at this point, before going into just some further objections or kind of questions with regard to the material. And then I have a second predictive argument on a related topic. So this is only the first half of the talk. So I'm doing 2 in a row here today. Okay, so what's the principle of confirmation used here in the case? So how is this thing working? And this is a little more technical, but I think it's important to, in a fuller version of this, I go into more of the technical details to make sure the thing really works, the argument. So let's back to the dartboard analogy. The the principle of confirmation used, as some of you might have heard of this principle, is called the likelihood principle. If some occurrence is much less surprising or improbable under one hypothesis, H1, than another hypothesis, H2, then that occurrence counts as strong evidence in favor of H1 over H2. And I give an analogy here in one of my articles. I give this analogy of how this principle works. And I imagine my brother used to live in Washington State, and we used to go hiking in the Cascade Mountains. So I imagine he's been up in the mountains, and I come walking up there, and below this cliff, it says, "Welcome to the mountains, Robin Collins." Okay? And I have two hypotheses, H1 and H2. One is the brother hypothesis. My brother was there and kindly arranged the rocks for me so it would welcome me to the mountains. And the other is the chance hypothesis. And what this principle says, well, under the brother hypothesis, that occurrence is not unlikely. Something I might even expect if he was a really nice brother, right, and very thoughtful about me. I would expect maybe he'd do something like that. But it'd be extremely unlikely under a chance hypothesis. So that, an earthquake occurred and the rocks fell and they fell just in the pattern just to welcome me. Okay? Now, so I claim that then the evidence that we find of the rocks under the cliff confirm the one hypothesis over another. And if you look at all kinds of cases across, like fingerprints on a gun, why do the fingerprints on the gun confirm or offer evidence that the defendant committed the murder? Well, you would expect the fingerprints on the gun if the defendant did commit the murder, but not expect him if he did not. So it's because of those difference in expectations, surprising under one, not the other, it counts as evidence. And this principle seems to apply across the board. So in the dartboard analogy, it's very surprising for the dart to hit so close to the edge on the dart thrower plus large bullseye hypothesis, but not surprising under the dart thrower plus small bullseye hypothesis. Therefore, by the likelihood principle, the dart hitting so close to the edge provides strong evidence in favor of the small bullseye hypothesis. Okay, and that's why we can infer to a small bullseye over the large one. Okay? And the same thing, this is just a repeat, but put in this next overhead, just a repeat of what I just said, except put in the case of the weak force or other constants. Constant being so close is very surprising, improbable under design plus large life permitting region. Constant being very close, not surprising under design plus very small life permitting region. Thus, constant being so very close to the edge strongly confirms design plus very small life permitting region over design plus large life permitting region. And so the same thing goes on, and you can work this out actually mathematically more rigorously. People have mathematical versions of the likelihood principle. Okay. And then that's one version. You can do it in terms of likelihood principle to make this more rigorous. You can also do an inference to the best explanation version. Only design plus very small life permitting region hypothesis explains why the constant both falls within the life permitting region and very near its edge. Thus, to explain the nearness of the constant, we should infer to design plus small life permitting region. And then design, or many universes, I could have included it up there. Plus small life permitting region hypothesis implies that we should find the unknown upper edge of the life permitting region relatively close to the lower edge. So what we get there this exactly parallels the fine-tuning argument. The fine-tuning argument here is based on the improbability of finding the constant near the edge. The fine-tuning argument is based on the improbability under a non-design, non-mini-universe hypothesis of the dart falling in the bullseye. Same sorts of lines of reasoning. Okay? the advocates of the atheistic single universe resist that line of reasoning. And so they claim that there's something illegitimate about it. And so an ongoing debate about that, which I've engaged in. But let's suppose we think the line of reasoning is legitimate. Then you can test the line of reasoning empirically. And that's the whole point of this. And I'm just going to put down here. Legitimacy of standard fine-tuning argument implies legitimacy of the above argument. Same moves are made, implies testable predictions. Okay. I'm going to see at this point, before I go on, is there any questions people have just right off the top of your head on this from the audience? Over here.
Could you summarize the result of your discussion there at Stanford?
Okay, the Stanford issue was on the mini-universes hypothesis, and I was asked, it was part of a symposium in which Martin Rees, Paul Davies, and some of the leading physicists and cosmologists working in that area, like on string theory and stuff, and they presented different takes on the mini-universe hypothesis. Martin Rees was advocating it, and several others. My take was this, is that even if there is mini-universes, you would still need to be designed. And there's nothing actually contrary to theism about mini-universes. I mean, God could have done it that way, if God's infinitely creative. So there's nothing contrary to theism. So I think it's a question about how much evidence do they have for this. I wouldn't necessarily buy into it, but even if they have lots of evidence for it, I think you would still need a designer to explain how there was, why there was those mini-universe generator, because you need all these special conditions to be met, and then I listed those conditions like an inflationary cosmology. And I gave sort of what I call a bread machine analogy. If you had a bread machine producing loaves of bread, and I used to have one, it's now defunct, everything has to be just right ingredients. To get a decent loaf of bread, I often have forgot the yeast, for instance, or did something else wrong, and I've got really bad loaves of bread that are hard. You could hit somebody over the head with them. Okay, so everything has to be just right to produce universes, and that was my take there.
Why is it true it has an infinite number of universes?
You mean all possible worlds? Okay, then you're not in a universe generator scenario, and then you're in a one like advocated by Max Tegmark. The problem there is that you would expect, if you look at the proportion of universes in which there's local islands of order, such as a local island of order, but everywhere else in the universe is chaotic, that seems to be much, much more probable than ones in which it's orderly throughout. So if you were a randomly selected observer, you would expect to find yourself on a local island of order and not in a uniform universe like this. And this whole argument was replayed back in early part of the century in explanations of entropy. And you can think of it in terms of physical entropy. It's much more likely to have local islands of highly ordered states than everything throughout be ordered. And if you give an analogy to that, it would be like a Scrabble board. If you shook the Scrabble board, it'd be enormously unlikely to have all the letters line up to make sense. And when they did, when some set of letters lined up to make sense, it would usually be a local phenomena. And so when there was some situation across the universes in which things were right for life to occur, intelligent life to evolve, it'd be enormously more probable for that to happen on an island. And so we should expect them to see a chaotic universe, not a uniform one. That's the sort of line of argument. So that gets into more technical details of that argument. That would be the response there. Anything on this particular argument?
Your next step is show us that testable hypothesis. Is that where you're going?
Well, I've already showed how you could draw testable predictions. Was that understandable to people? It predicts the upper edge of these life-permitting regions. So we know the lower edge of the life-permitting regions, like we know the lower edge of the bullseye, in the dart thrower analogy. So if you put on your spectacles, you were seeing these darts come in, you would predict, you would say, if I put on my spectacles and can see the upper edge, it's going to be very close. And if you didn't find it very close, you would have, it would be evidence against your hypothesis of a generic dart thrower. So if a generic dart thrower, if as an explanation, you would expect to find it very close.
I guess my question is the word testable on that last transparency. You're saying now that you have that analogy, there's actually some further ways to test the analogy?
It would actually lead to predictions that you can actually go out and, so if the advocates of fine-tuning are right, what we should expect is like when we find a lower edge of a life-permitting region and we find the constants very close to that lower edge, but we don't know the upper edge yet, we should expect the upper edge to be fairly close. So we actually have something we could go out and test. Now, there's a question, does it falsify? Let's suppose we didn't find that, and would it falsify it? And that's where it's not quite clear it does, and that maybe I should go into next here. And that's number 2 here. So that's a kind of question I think you might have been hitting at. What if you didn't find that? Okay, is everybody else clear on that? Because that's the key point about the prediction.
I'm not sure, but my question, which is sort of a tag-on to his, would be what would that research look like to either falsify or validate your prediction?
It would look like, as we did more study of the nature of physical laws, and it wouldn't actually be going out and doing a new experiment. It would be a more theoretical enterprise where we look more deeply into the structure of laws and try to derive consequences from them. So when all these fine-tuning arguments are almost entirely based on doing various sorts of theoretical calculations. So for example, one I mentioned in the article I referred to in God and Design is one by Heinz Oberhumer and several other people involved with that on the fine-tuning of the resonance states of carbon atom and oxygen. They have to be set just right in an atom, and they're dependent on the strong nuclear force, those states, in order to get sufficient carbon and oxygen produced by stars for life to occur. So what they did is, and it took them they came out with this around the year 2000, where they have more and more advanced codes to do this, which are computer codes that do these calculations. Some of them are fairly complicated. So they calculated what would happen if you made a slight change in the strong nuclear force and the consequences for this stellar production, a very complicated calculation, and they came out with a certain result. So that's a theoretical calculation. So what I'm saying here, as we understand the weak force better and things like that, what we would expect then under a theoretical calculation is that the upper edge of the life-permitting region would be fairly close to the lower edge.
Just to restate that, I'm, as a non-technical,
Mm-hmm.
I don't have a scientific background, but what you're really saying then is as more and more research is done, the prediction that you've made is going to be proven true by future findings. You would predict that is going to show this bullseye is smaller and smaller, and in your example, just
Or it would only show it's not necessarily smaller and smaller if this hits, if we go back to our original thought experiment, if this hits within a few hundredths of an inch of the edge, okay, just think about our original thought experiment, and we put back spectacles on, then we would expect that to be within a few hundredths of an inch larger. We wouldn't expect it to be a whole foot over here, because that wouldn't explain the nearness to the edge. Okay, so likewise, if we find the weak force very close to the lower, let's say within a distance d, and I had 1/1000th of an inch foot in my example was on my scale, then we would expect to find the upper edge not within a billionth or 10 billionths or something like that, not like another foot away. Okay, question here.
Robin, is not your range an indication of the accuracy of a dart thrower? If you were a perfect dart thrower, you'd have the same range all the way around where the dart is the size of the pulse.
A perfect dart, you don't know where the perfect dart thrower would hit it might hit anywhere. If all of them were optimal conditions within the bullseye, then you would expect it to hit anywhere in the bullseye. Now, on the other hand, if one of them is completely optimal, then that would be the life optimal range. So you'd have to move from life permitting range for your bullseye to life optimal range, which is another sort of fine-tuning argument that, for example, Michael Denton talks about. Okay, I'll take a couple more questions, and then I want to move on to my next thing over here.
Estimated time frame for the possibility of determining that upper edge. You mentioned it's more like thought experiments and fine-tuning of calculations. Are we years or decades away for that sort of thing?
I don't really know. A lot of these things are difficult to do. I mean, these stellar codes, like, for example, when I worked with Oberhumer and then one of his colleagues, Helmut Schlattel, through email and all this stuff when I was working on the article. And he initially gave me, I was looking at the question of a deuterium star and whether that would be feasible or not. And when he ran it through his old codes, he came up with one answer. He came up with quite a different answer when he ran it through like the most recent codes. And we had confidence in the most recent answer. So some of these whole issues are very complicated, what goes on. Some fine-tuning arguments are very straightforward. Okay, like you have, if you decrease the strong force, what happens? Well, strong force holds protons and neutrons together in a nucleus. Protons repel each other. And that's the electromagnetic force. So if you decrease it by very much, nuclei fall to pieces. That's straightforward. Everybody can see that. And there's no complicated codes. Others you need more complicated codes for. And so it just depends on the case. But for me, it's a theoretical interest that you actually can get predictions. It looks like a metaphysical hypothesis. Initially, it's all metaphysics. But now, in ways you wouldn't anticipate, you maybe can get predictions from these things. So it kind of counters that objection.
Partly bringing that up, if it's within a reasonable period of time or within, let's say, a lifetime, then you're at risk. But if you make a prediction that will take 10,000 years for anything to ever
Right.
happen, it can sound like, oh, it's kind of like maybe what Darwin did. Oh, in 2 years, I'm sure we'll find it.
Well, the risk is only the odd thing about this. I'm not sure how much you could always, there's a backup strategy. One could always say, there's two things at risk. One is at risk is the fine-tuning argument. Because you could still believe in God and not believe in the fine-tuning argument. And so it's not theism itself or design itself at risk. It's the more fine-tuning argument. But you could also, it's not completely falsifiable, because even if it turns out to be false, this always happens in science. Falsifiability is far too quick in science. Most theories are not really falsifiable, as we find out with evolutionary theory. You find something, they make a new story up. So you also can do the same thing here. If the prediction turns out to be false, let's say in several cases, one could always adopt a non-generic design hypothesis or reject assumptions underlying the fine-tuning. So a non-generic one would say, oh, the designer really likes edges. And the designer is, making them near edges. We don't have to go there yet. But the interesting thing is we do have an expectation from a generic one. If you look at inflationary, when they're testing inflationary universe scenarios, that's what the scientists are only looking at, generic inflationary scenarios. If you modify them, you can get almost anything you want. Okay, question over here, and then I get way back there, and then I ought to go to my next thing here in a minute.
Do you suggest that primary reason for questioning the validity of the atheistic single universe hypothesis is that there is no testable predictive consequences?
Well, that's not the primary reason. I think that it's this principle of confirmation. It's let me go back a couple slides on that. What I do is do a principle of confirmation here.
Could you repeat the question?
Okay, the question is not drawing testable consequences, is that the primary reason for rejecting the atheistic single universe hypothesis? I don't think so. I think it's more analogous to the case of the rocks on the cliff. So I think it really is improbable, and I think you can make that case. And in the right sense of improbability, what's called epistemic improbability surprise, that it is very surprising for all the constants to be within this very small life-permitting range, but not surprising under the design hypothesis. So I think just by that's called the likelihood principle, a principle used all over the place, it follows that the fact you find them in that life-permitting range is strong evidence for preferring the design hypothesis over the atheistic single universe hypothesis, just like we do with the fingerprints, just like we do with the case of rocks on the cliff. Strong evidence, though, is not the same as saying we've proven it. Fingerprints could be strong evidence the defendant is guilty, but you might also have other evidence countervening that. So it could be strong evidence, but somebody would say, well, we have 100 reliable witnesses that saw the defendant somewhere else at the time of the murder. So I only claim we can establish there's strong evidence for theism based on this, using this standard principle of reasoning. Way back here.
Former President Jimmy Carter wrote to Stephen Jay Gould in his book Wonderful Life
Uh-huh.
about the possibility of probability.
Uh-huh.
But in Stephen Jay
sample of 1. Would you comment on that, please?
Okay, I think that is wrong. And I think we have to make a distinction there between what's called epistemic probability and okay, let me first back up. That's one of the standard objections to the fine-tuning argument raised by people who advocate the atheistic single universe hypothesis. So when you buy into the validity or the legitimacy of this fine-tuning argument, you're buying into that you can really, there's some notion of probability, at least if you buy into that version of it. And I think you can talk about epistemic probability, which is degrees of belief, degrees of surprise. That's apart from having many, many cases of that sort of thing. So in cases of science, the nearest cases of this would be cases of science in which you actually do use, like in confirmation of theories. You find one theory predicts a very precise value for a parameter and another theory does not. And then you can say that it's very improbable for it to have just that value predicted by the theory by chance. So I'm not giving you a very good answer here, but let me just go back. Let me back up here. That example's not, I think that the response there is you can talk about epistemic probability. That's the main line of response. Epistemic means degrees of belief or surprise. So you can talk about that when your case of your sample is 1. So here you have a case of a sample being 1. Let me give you a more homegrown case. Let's suppose you have a billion-sided die, okay, all symmetrical on every single side. You roll that die, and it comes up on your favorite number, let's say 105. We could say that was very improbable unless somebody made the die to be biased in that direction. It would be very improbable on its own, even though there only have one time you ever rolled it, and after you rolled it the first time, it blows up. So you've talked about probability in that single case there. You don't have many cases to be talking about. And the kind of probability there is surprise, and there's vast literature on that. It's epistemic. There are degrees of belief that we would have, given every side is equal, that would come up on that side versus all the other sides.
What book would you recommend as far as,
Of the epistemic probability? I don't have a book right off. Swinburne's explored this. Alvin Planning has explored this. If you look at my website, www.messiah.edu/R Collins, and a lot of those fine-tuning arguments that I offer there, I reference the literature on epistemic probability. But that's going to be the key here. It's going to be a different kind of probability, especially in Reason for the Hope Within. I talk about that by Michael Murray, editor. It's an article I have on that on fine-tuning. I'll take one more question, then I want to go into my second argument.
Don't you have a way? You've got approximately 80 anthropic principles. You're giving me an example to get it.
80 of anthropic cases of fine-tuning, you mean?
Yes. And you made the point that very many of them, we know a lower boundary.
Right.
But we don't know an upper boundary. And you're making predictions. That's what this discussion is
Right.
about. But are there not anthropic cases where we know both a lower and an upper?
Yeah, there is cases like that.
And when we compare what we're predicting here, where we don't know the upper boundary, does the values play true to the ones where we know both edges? Did I make myself clear?
Yeah, what you shouldn't have, what you're really asking in those cases, does the constant fall really close to one edge, and you know the upper edge, but it doesn't fall close to the upper edge? That's an interesting question. I don't know of anywhere you find that sort of disconfirmation. So what you're asking, let's suppose we knew the fine-tuning of weak force already, and you had the upper edge was billions and billions of times way up there, and the lower edge is here, and we know that that's the upper edge for sure. We know for sure that there's not some subtle physical process going on such that there's actually the upper edge is even lower than that. So you can have a calculation of one upper edge, and you know that beyond that it's not life permitting. But there might be other reasons that even if you didn't increase it that much, it would still not be life permitting. Like, let me just complete that example, because you could have case of gravity, for instance. I have a calculation in there. There's one argument why gravity, the easiest argument to make, if you increase gravity like by a billionfold, you can't get, which is not that much compared to the range of forces, all life forms that could be intelligent would be crushed. So, and even you couldn't even have a planet. No planet could sustain them. So that's one just straightforward argument. But there's other reasons that are much more subtle to think that even a 1,000-fold increase will mess up the possibility of intelligent life, and that's based on how stars operate, the stability of stars.
You end up with the same problem when you apply it to the lower edge of
There might be a closer lower edge.
In other words, you're saying that you can make a testable case and find out which of the four hypotheses
Right.
is most likely to explain. But you've got situations where you know an upper and a lower. And if it doesn't answer the question as to which of the four hypotheses, because there are problems with
Sure.
knowing the upper edge, don't you have problems theoretically knowing the upper edge of the ones where you only know the lower edge?
Yeah, that's true. I mean, you're going to have to do more calculations, but that's all the good for making it a scientific hypothesis. We have a scientific research program here. So in terms of making it a scientific hypothesis, that's just what happens in science. We always have other alternatives we have to explore.
But has anybody applied this argument to cases where we have
No, I mean, this is arguments. This is the first time it's out in presentation form. So, I mean, wait 10 or 20 years. Okay. Okay, let me go on to the next talk. John, do I use... we started 10 minutes late, so do I have extra 10 minutes? Okay, I'll be definitely done by 10:45. Okay. So that last question, I think all the better. We just have something to work on for scientists. Right. Okay, now here's going to be another, it's a fine-tuning related hypothesis. Remember, there is the mini-universes hypothesis, but there's also a parallel to the mini-universes hypothesis, and this is really talk 2, and I should be able to get done with this in time. And there's the mini-planets hypothesis. So some people, they look at the origin of life and other things like that, and they say, well, that is just highly improbable. And they don't want to infer to design. So a lot of people admit that occurrence of life here on Earth is highly improbable. Such as, but then what they say in response to that, if they don't want to go to design, they say, oh, they're just mini planets. I mean, after all, there's 300 billion galaxies in our universe, and there's 300 billion stars per galaxy, and in a mini cosmic theory, such as inflation, the universe might be 10 to the 80th power times as large. So there might be so many planets out there that even if on any given planet it's very small, the probability of life, eventually it's going to occur, and that's not even taking into account mini-universes. So this I call the mini-planets explanation for the improbability of evolution. And so here's the kind of basic claim. Suppose that the evolution of intelligent beings such as yourself is enormously improbable in any given Earth-like planet. Given this, many are tempted to explain our existence by appeal to design. Others, however, reject design and appeal to a mini-planets hypothesis. Given that there are an enormous number of planets that could sustain life, eventually one will evolve intelligent beings such as ourselves, even though the chance of this happening on any given planet is very small. Now, my main thesis on this second talk is that this is testable in some ways. I will argue that given that our evolution required many improbable steps, it wasn't just one step, but many, the mini-planets explanation leads to testable predictions that are known to be false, or very close to known to be false. We will start with an everyday thought experiment, and the calculation I give, I just say, close to no one. Barrow and Tipley present an argument thinking it's not false, but I disagree with their argument. So the main calculation below, along with some of the ideas I owe to Barrow and Tipley, are the anthropic cosmological principle in these pages. But I put it to a different use than they do, and I've made the calculation much more sophisticated. So here we're going to start, because it's somewhat of a technical argument, so I want to start making this, as I did before, into an everyday thought experiment. So we're going to talk about two somewhat foolish people, Jack and Jill, who want to buy a $2 million house in California. They've noticed the real estate price has been going up. And they intend to finance it by each winning a lottery with a $1 million lottery jackpot. Jack buys one ticket per year in the California lottery. I don't even know, do they have a lottery in California? Yes. They do, okay. And Jill does the same thing for the Pennsylvania lottery, with each ticket having a 1 in a million chance of winning. Chance of both Jill and Jack winning in first year is 1 in a million times 1 in a million equals 1 in a trillion. Chance in 2 years is 2 in a million times 2 in a million equals 4 in a trillion. It's pretty straightforward calculations. Chance in 3 years is 3 in a million times 3 in a million equals 9 in a trillion. Chance in t years is t squared over a trillion. Okay. And I just note here the probability calculations above are following are only accurate if we assume that it is improbable. It is very improbable, there's a double repeat, for any given individual in our thought experiment to win the lottery in t years. So it's not going to be probable in either one. Then it becomes accurate. Okay, that's just a side note for people that are technically sophisticated in the audience. Now I change the example, and I suppose Jack, Jill, and Jane each bought one lottery ticket a year in different stage, each ticket with a 1 in a million chance of winning a $1 million jackpot in order to jointly buy a $3 million dream house in Monterey, California. I'm not sure I spelled that right, but leave here or there. So we get 1 in a trillion for each of them winning, and then we get, in 2 years, 8 in a million trillion. You just multiply 2 million. And then in t years, t to the third over a million trillion. Okay, fairly straightforward. And if we generalize to in individuals doing this, all going together, now in really foolish individuals, chance of all winning in t years is t to the nth power over a million to the nth. And the important thing to note in the above example is that the probability is proportional to the nth power of the time. In general, no matter what the probabilities of winning for the lottery ticket are, the chance of all individuals winning is proportional t to the n, given that it is improbable for any given individual to win in t years. So the probability increases exponentially, not just a flat linear way, but exponentially with time. Okay, that's the key thing. It increases very quickly. Okay. So if they're doing this, it's much more probable later on, especially the more individuals you get, that they'll all win. All have won by then and can buy their house than early on. And you can sort of see that if you think about it, because you have like Jane and Jill, the probability of them both winning in the second part, they could either both win in the first half, and they would have won by the second part, or one win in the first half of the first year, say there's 2 years, and then one win in the second year, or both win in the second year. So there's many more chances altogether of them both winning in 2 years. Now bear with me on this example, because now we're going to go to the mini planets version, and then we're going to do the correspondence over. Now we're going to consider our mini planets thought experiment. So we're moving on to this mini planets business. And there are trillions upon trillions upon trillions of duplicate Earths. So there's Janes and Jills all throughout our cosmos. And they all live exactly 100 years. If we look across these planets, there will be many more in which they jointly buy their house in the latter half of their lives than the former. For example, as we look at all the planets in which they finally bought their house. So we only look at those planets in which the house was bought. And if we look at only those planets, we find out in the latter half, we find out the probability of them both winning by 50 years, so we assume they win 100, all live 100 years, and they start when they're born buying these tickets. They're silly child prodigies. And we get 50 squared over a trillion, whereas 100 years, we get 100 squared over a trillion, which is 4 times as large. So, but it turns out, thus among those planets in which Jack and Jill buy their dream house, there will be 3 times as many in which they buy their house in the second half of their lives. Why 3 instead of 4? Because 1/4 of the probability is put to the first half, 3/4 to the second half to make the final at the end of the 100 years 4 times as large as right in between. So it actually turns out to be 3, but that's not really very relevant. All you need to know is it's much larger, much more chance that they'll have bought their house in the second half of their lives than their first. Now, application of many-planets explanation of the improbability of evolution, a prediction. So once you got that thought experiment, it's going to be much more likely in their house in the second half than the first half. Once you get that key point, we're going to move on to giving the correspondence with the many-planets explanation. Now consider a simple model of the evolution of intelligent beings similar to ourselves. In this model, the evolution, and the IBS, intelligent beings similar to ourselves, requires n improbable independent steps, where an improbable step is a step that is improbable within the maximum time, Tm, in which the evolution of such beings could occur, which we will assume is the lifetime of our star like our sun. So if we have an evolutionary model, we have all these independent steps must occur to get us. The maximum time for evolution to occur across these planets is going to be the lifetime of their sun, which we're going to assume is a kind of sun called main sequence sort of star like our sun, which is about 8 billion years. Further, suppose that the probability of each step is constant. So these are all presuppositions Barrow and Tipler also use in their variation of this. Roughly, this means that for each step, if twice as much time goes by, it is twice as likely to occur. If 3 times as much time goes by, it is 3 times as likely to occur, just as in the case of the lottery example. So in the case of, for any individual in the lottery example, Jane, if she lives 2 years, it's going to be twice as likely for her to win the ticket as 1 year for each ticket. Not for all of them together. That's a different matter, as we already talked about. 3 examples of potentially improbable steps are the origin of life, the formation of the first eukaryote cell, the evolution of multicellular organisms, and the evolution of sex. I mean, that's 4 maybe there. Now, each step could be thought of as winning a lottery. In order for IBS, or beings like ourselves, to occur, all independent steps must occur. That is, all lotteries must be won. So then, just as in our lottery example, we have a calculation we can perform, and you get the same sort of thing. It's proportional to the time allotted of all lotteries being won, of all those steps occurring, is way, way more improbable. It increases, the probability of all those steps occurring increases exponentially. That means if you look across those planets, here's the formula, same as the lottery example. If you look across those planets, it would be, if the maximum time is 8, that would be like the lifetime. It's equivalent to the 100-year lifetime of Jane and Jill. That's the maximum time evolution could occur. It's way more likely, if there was 2 steps, it would be 3 times as likely for evolution to occur in the latter half of the lifetime of those suns than in the former half. If there was 30 improbable steps, it would be 2 to the 30th. That is approximately 1 billion times more likely. This means that if we assumed a many-planets hypothesis to explain away the improbability of that IBS evolving, and if we looked across all those planets in which IBS evolved, we're only looking at those planets now in which the evolution has occurred. Majority of planets, since it's so improbable, nothing's going to happen. So we're only looking at those planets in which it actually happened. 1 billion times of many would have evolved in the latter half of their sun's lifetime than in the first half. Thus, if we consider ourselves a randomly selected IBS, intelligent being such as ourselves, we would expect with overwhelming probability to have found ourselves having evolved in the latter half of the lifetime of our sun, not in the former half. The mini-planets explanation of our evolution, therefore, could be thought of as making an empirical prediction that turns out to be falsified, at least given that we have evolved by unguided chance plus natural selection, and given that our evolution required many improbable steps. And I won't do it right now, but if people want to ask me the question about why take us as a randomly selected observer, well, that's usually what you do when you do probabilities. It's like me getting cancer if I've been smoking for 20 years. Then I consider myself an average Joe and ask, well, what's the probability if I'm a randomly selected average Joe? And that's what I base my expectations on for me getting lung cancer. Same thing going on here. So we get a prediction that seems to turn out to be falsified. And then I have just several other ways of putting the conclusion. Put differently, we should be very surprised to have found ourselves to have evolved in 4 billion years, around half the lifetime of our sun, given this mini-planets explanation of our evolution. Consequently, although the mini-planets hypothesis takes away the enormous improbability of intelligent beings like ourselves evolving, it does this at the cost of introducing another significant improbability, namely our having evolved in the first half of the lifetime of our sun. And then, just as a side note, and work this out in a paper form, I've done it for a much more sophisticated model of our evolution in which the steps are dependent on one another. So they're not all independent, because clearly you can't have a formation of a eukaryote cell until you get life starting. So the one step is dependent on the other. But even if you make them dependent on the other, the calculation still works out to be the same sort of conclusion. So it's a fairly robust result. Okay, and then here's the various responses to the above argument. One response to the above argument is to give up the mini-planets explanation of the improbability of our existence under naturalistic evolution, assuming it is very improbable. This, however, leaves, so if you were a naturalist, one thing you could do is you could say, oh, it's not really, evolution is, you could say, yeah, I agree it's very improbable, but I'm not going to explain it by the mini-planets hypothesis. But then I think you have an enormously strong confirmation theory argument based on the likelihood principle for design in place. If our existence is much, much more improbable under naturalism than theism, then it follows from the likelihood principle, that principle I talked about before with rocks under the cliff analogy, that our existence offers very strong evidence for design. And I have this irresistible aside here I have to give, because Stephen Gould, the late Stephen Gould, I don't think never got this point. The likelihood principle refutes Stephen Gould's argument that if human beings must be an accident, since if we replayed the evolutionary tape, it would be very unlikely for beings such as ourselves to evolve. The likelihood principle would say that since our existence is not improbable under design, if Gould is right, that it's very improbable under a kind of a naturalistic scenario, then our existence provides strong evidence for design, not what he thinks, it provides evidence that we're an accident. So I think it's just the reverse conclusion. But that's an aside that I couldn't resist because I bring it up in this context. So one response is to give up the mini-planets explanation, but then I think you're left with a good case for design then. So given that one does not abandon the mini-planets explanation of the improbability of our evolution, we have 5 options regarding how to respond to the above argument. You can deny that the maximum time for intelligent beings such as ourselves to evolve is significantly greater than 4 billion years, and hence adopt something like Barrow and Tipler's doomsday conclusion. So Barrow and Tipler in the cosmological anthropic principle talk about this simple model of evolution, an argument they get from Brandon Carter. And they conclude not the theism like I'm doing, and that the mini-planets explanation is false. They conclude that, oh, that means that really, since the maximum time of our evolution to occur is not 4 billion years, but much, much shorter, and therefore they predict what's called the doomsday conclusion. There's this whole literature on doomsday arguments, that if that's right, then the stability of the sun, unlike what we think, or the stability of the Earth's atmosphere, is not much greater than 4 billion years. So we would expect to, within maybe 1,000 years or so, everything to be disrupted and us all to cease to exist. So, because that's the maximum lifetime of Earth-like planet in which beings could evolve is much shorter than this 8 billion years. So that's one conclusion, and I don't think that's a well-based conclusion, but that's one way you could go. You could claim that although the evolution of beings such as ourselves is enormously improbable, it does not require many improbable steps, not at least in the sense needed for the argument. Deny that our evolution is enormously improbable, either because the evolution of IBS under neo-Darwinism is not highly improbable, or because evolution is preceded by some other mechanism. Deny that we have evolved. So there's various ways of responding to this, and I went through those very quickly. So I realized all I want you to get out of that is there's various ways of responding, but I want to look at the conclusion here now and stress this conclusion. One way or another, one can scientifically test the many planets explanation of our evolution by scientifically determining whether, one, our evolution did require many improbable steps, and two, whether the lifetime of the sun provides a good estimate of the maximum time for evolution to occur on an Earth-like planet. If we find out that these two conditions are met, then the many planets explanation leads to a prediction that is known to be false, or a prediction with high probability. Namely, that with overwhelming probability, we should expect to find ourselves considered as randomly selected observers to have come into existence in the latter half of the lifetime of our sun. So the significance of this is that we actually can, here we have of the improbability of our evolution, we have a many planets explanation, we have theism. We can actually now go out and test it. They look like metaphysical hypotheses, but they actually have testable consequences. So in this one, the way you would test it is by checking if our evolution actually required many improbable steps. That's going to be the future development of science. And whether this is the maximum time for evolution to occur is really the lifetime of a sun. I'll take questions. First questions, if people have questions of understanding the argument first, because, okay, I don't see any hands going up there.
What happened to the second law of thermodynamics in all of this? I mean, that speaks very strongly against time being a factor in favor of evolution.
Okay.
Where does that get calculated in this probability? Repeat the question, please.
It's where is the second law of thermodynamics? Well, the usual response of people who would have, one thing I would say, that's a separate discussion whether evolution is compatible with the second law of thermodynamics. Assume it is, and the usual assumption is that the Earth is an open system, because the second law only says that the amount of usable energy or the amount of order in a system has to decrease with time. The system becomes more orderly if the system is a closed system. But the Earth is not a closed system. It's an open system. You have the sun. So that's the first response to that an evolutionist would give, a standard response to the thermodynamic second law objection to evolution. So then you're going to have to give a response to that response. Something like, well, you'd still need something to focus the energy, to make it, to convert it from the sun's energy to convert it to an evolutionary process. And well, the whole point of evolution is they claim to have a mechanism to do that. So the strict second law of thermodynamics, strictly held, does not contradict the theory of evolution, though more sophisticated considerations might be thought to contradict the theory of evolution. And that's because the Earth is an open system.
The answer to that is twofold. First of all, they assume the universe is an isolated system. So the second law would apply to the ordinary universe. Now, the idea that the Earth is an open system, that's the problem. That's not the answer, because the ultraviolet light coming from the sun, there's no ozone layer to protect the Earth. But that ultraviolet light is not constructive, it's destructive. That is simply not an answer.
Well, that would need, you're giving a more sophisticated argument. You're not strictly using the second law here. You're saying there needs to be a mechanism to focus the energy of the sun. It's like the energy in a gas tank, okay? Every time you run a car, you're increasing the amount of entropy in the universe. But if you just light a match to the gasoline, you don't get order. You'll have to focus it somehow through the mechanisms of a car. But that's another separate argument. Can they give a way of focusing this energy? Do their scenarios on the origin of life give an adequate way of focusing this energy, somehow bringing in information to make life possible? And this is where like Bill Dembski or Steve Meyer have tried to address this question, which is not strictly speaking the second law, but a different kind. You're talking about whether you can get information out of nowhere, out of just chance processes like the typical evolutionist claims. And that I would have to leave for my esteemed colleagues, Steve Meyer, Bill Dembski, and others. I see Bill out in the audience over here to address that question. But they'll hit people back here next.
I understand, my understanding is that the age of the sun is, we're actually pretty close to the end of the life-sustaining lifespan of the sun. So how do you understand your prediction in light of that? Are we,
Well,
I'm not an expert on the field, but I thought we only had about 1 billion years left.
well, even 1 billion years, if there was enough improbable steps, because it goes up exponentially, even 1 billion years would make it much more probable that we would have evolved in the last 1 billion years of the lifetime of our sun than much before. So you'd have to have, if you had a lot of improbable steps, then it would still provide a good argument, even if that's right. Because what you're saying is the sun is its energy output's increasing, and eventually will go to a red giant, et cetera, et cetera.
Doesn't that also provide another way, though, of proving?
Jed is working on getting a microphone for the questions.
Okay, the question is concerning the lifetime of our sun. And one response is that our sun doesn't have nearly as long of a lifetime as 8 billion years for at least a lifetime such that intelligent beings could evolve, because it will become a red giant or will have other instabilities. And so it's maybe only 1 billion years left. And so even if there's only 1 billion years left, I responded, if there was enough improbable steps, if evolution required enough improbable steps, that it would still be very unlikely for intelligent life to evolve in the first 4 billion years instead of the last billion years, because remember, this curve is exponentially increasing. So it still becomes much more likely. So this argument still holds as long as there's a lot of improbable steps.
But as long as we don't know the upper bound, or this kind of goes back to your.
Well, that's a testable, so you can test this argument out, okay, by checking whether it's falsified or not, many planets hypothesis. So the way you'd have to check it is there's scientifically something to do to check it out. Check the upper bound of the lifetime of our sun. Check the number of improbable steps required for evolution. So the whole point is there's testable consequences, not that we have them all in place yet.
I have a microphone
Way
here.
back over here.
Let me bring you the mic.
So my point is testable consequences, not that there doesn't need to be scientific work done. But that's what makes, that's one of the features that scientists will claim makes a theory scientific. There's things you can test about it. It leads to consequences. And that's what I'm primarily interested in here, not the results as much, as that has those consequences.
Okay, just to recap a little bit now, we're dealing with the idea that complex life, intelligent life, is more likely to occur further on in the evolution of a star on a planet such as ours. And
given that there's many improbable steps.
Right, and given the idea that the life of our star is perhaps somewhere around 8 billion years, you're saying that we're kind of around the midway point here where we've got sentient life such as ourselves. But the thing is that by the time our star actually hit its midway point, which I'm not exactly sure how much time before, say, the formation of the Earth, the sun was essentially the same as it is, maybe at, what, 500 million years or so? Mm-hmm. That, if you add the 500 million years onto the 4.5 billion year history of our planet, we're at 5 billion years, and complex life, such as what we see in early Cambrian and Precambrian, where we start getting above the level of bacteria and single-cell organisms, is already at the halfway point of our star. And from that point onward, we have a rapid increase in complexity within the areas of, if I understand your argument correctly, points at which the probabilities start to increase that this type of life is going to occur. So it seems to me that actually we're seeing the complex life at the wrong time rather than at the right time. I think that your argument would be much stronger if we were looking at the fact that we were only in a 2 billion year history of our sun, rather at this point in 5.
Okay, that is going to depend on how much longer we have for life to evolve. It depends here on the steepness of this curve. So the argument actually depends, and that's what it should if it's, let me get an overhead here where I can make this point a little. Here you'll see the advantage of not using PowerPoint, because I can actually now draw something spontaneously. So I feel so primitive. I'm probably going to be the only one using not using an old overhead projector up here. Even Hugh Ross has moved now. You've moved to PowerPoint. So, here's the 4 billion year mark. Here's the maximum lifetime for evolution to occur, and here's the lifetime of our sun. It depends on how the curve, it says it's exponential, a t to the nth power, and there's a lot of steps. That's going to increase really, really rapidly towards the end. I'm not a very good drawer. So if it's really, really rapid, we would expect our existence to have come into being really close to the edge of the maximum lifetime. So if we think the maximum lifetime is even 1 billion years off, that's going to be contrary to expectations. But if the maximum lifetime is like 100 million years off, then maybe you're right, if there's a lot of improbable steps. So there's something to empirically look at here now. It's a possible way of empirically testing the hypothesis. It's something for scientists to do.
Yes, let me bring the mic back to you.
Those are really interesting results, but it's a fairly simple model.
Right, it's a very simple model of our evolution. That's true. And I said it works under a more robust model, but even the more robust model, when the steps are dependent on each other, it's still a simple model of our evolution. This is really simple.
Right. But there's quite a bit of detail that has come out in the last 10 years, 15 years on the fossil record in terms of when life first occurred, Cambrian explosion, how narrow the band was of time in which that explosion started, and some other things like that. And I think it's really interesting. You've talked about improbable events, and yet the fossil record would suggest that life occurred very early in the Earth's history over a fairly short time band. Otherwise, it occurred very soon after the Earth got cool enough to even conceivably have life. And then the Cambrian explosion occurred over a very short time band. So what an atheist would say, and I'm not one, I call you brothers here, would say that, okay, well, the assumption is that these are very likely events. They're not unlikely events because they occurred over such a tight time frame. And therefore, if you make the assumption that they're making that God didn't do it, that there must be some mechanism, we just haven't found it yet.
Right, well, see, I think that begs the question against there's two ways of calculating this looking at this improbability. One is by looking at the fossil record, but that assumes that God didn't do it. That assumes already that intelligent design is false.
No,
okay.
Not from my point of view. But.
Well, if just looking at the fossil record, because if God was involved in it, we couldn't say what the probability is under purely naturalistic mechanisms. You have to assume, as you just said, that God wasn't involved in the process to say that the fossil record indicates how likely it is under purely naturalistic processes.
But I have two directions here. One is that we want to develop a flow of thought that is apologetic in a humble but convincing way to our atheist friends. And then the other is that we have a set of data there that must constrain our model. And I think that we need to honor that data and think about what of how God intervened in.
Well, yes,
to make
it
these
could
things
tell us
happen.
how God intervened, but it couldn't tell us the probability. Let's say, what's the probability of, here's one argument somebody could give. Well, the occurrence of life must not be very improbable under purely naturalistic processes because, after all, it did occur, and it occurred in fairly short order.
Right.
Well, from somebody who it was an open for a person for whom it was an open question whether direct design of some sort of God intervening in the evolutionary process or the formation of life in some way was an open question whether that would happen. It would be an entirely unconvincing argument because they would say, well, we can't deduce from the fact that life occurred in such short order that it's improbable because as far as we know, God could have created it. So you would have to, the only way you could read from when life occurred and when these various steps occur, its probability under a non-theistic hypothesis or non-design hypothesis is to assume design didn't happen, at least in the way that people, in terms of God intervening in some way.
Right.
And
Yeah.
so I think the only way that's neutral of trying to get those estimates is by theoretical calculations, which are very difficult to do. Looking at all the plausible scenarios of the formation of life and looking at what the chance would be.
Right. Right.
But anyhow, that's my response. And
See, I see a hand down here in the front left. And then maybe,
Right here?
Yes, and then I'll take maybe one more question.
yeah, one
then
more
we'll shut
question,
up.
so I don't want to over.
Well, you have time and then you have number of events. So kind of you're getting at intervals. Have you estimated what those intervals, I mean, everything by analogy to your lottery gets down to like discrete intervals where there's a probability within an interval. Have you estimated what, I mean, it's not just numbers.
For a continuous event, you mean continuous?
Well, it's not continuous because at least
in the lottery example it isn't, but if you use it as a continuous parameter, the same result comes out as
but
t to
that
the
would,
n.
okay, but then everything depends on what that parameter is, right? Because you're sort of going to an interval form.
Well, Barrow and Tipler do it for a continuous parameter. I did the lottery example because that's easier for people to get a grip on.
I'm not saying it's not true, but I think it really focuses down to what that parameter, the probability per interval.
Per unit time, right. And
right.
And this more sophisticated model, I addressed that question.
I mean, because in fact, your curve is not going to go up forever. It's going to, at the end, some point, be fairly flat as a function of time because you've hit the cumulative distribution.
Well, you hit the maximum time, right.
So
there's additional complications that are not included here.
I think you're talking about the beginning of the curve and that it depends that the probability per interval is small enough so that then we're on this sort of still on the upslope, we're on the linear, or exponential increase portion.
Right.
And then it's a strong argument. But I think someone might say, and I don't know, I haven't done it, but what are the ranges of those, probabilities per interval that make this an argument?
Right, and I have that addressed in a more sophisticated version. But and I think you're right on that. So I think the overall, all you're justified in saying here from this presentation is not that all this works, because there's all these different sorts of things going, different sort of considerations to be taken into account. But my overall point, and I just come back to that as summary, my overall point is that things that look like purely metaphysical hypotheses, there's interesting ways that you could potentially draw predictions from them. And so if that's right, there's something for scientists to do. And that means that the ID program, it's wrong or highly questionable to shove it off into just metaphysics and not science. And like there is an article by Max Tegmark, for instance, that is published in a physics journal, the Annals of Science, and it basically advocates that every possible universe that there could exist, and there's an explanation for the fine-tuning. And how did it get in there? Well, maybe it shouldn't have got in there, but it looks purely metaphysical, but his claim in the article is it's scientific because you can draw predictions. I don't really think he gets predictions out of it, but he claims that, and at least tries to make a plausible claim for that. So that's my overarching concern here, is that it's far too quick to say these things are purely metaphysical.
One last
that's it.
question. Then.
Thank you for your attention.
My question was concerning the parameters that we're talking about you're talking about different ways of measuring parameters for life. And the question I have is for when you're talking about adaptation, where you have systems or substances or life forms that adapt, how do you then establish the parameters? For instance, taking a very simple example, me in my current form wearing this shirt that I'm wearing and lightweight pants, if you took me and you put me in the Arctic, I would die very quickly because of exposure. However, I do have the ability that I could adapt to that environment, so my current parameter would be a small temperature zone, ranging from this temperature to that temperature, whereas if I slowly move up to another temperature range, then I could now withstand something higher. So how do you deal with establishing those parameter conditions with substances in those parameters that have the ability to adapt?
Basically, that was the more sophisticated model I mentioned, where you have to assume that the probability distributions don't fall off with the changing environments. In general, don't do this. Now, maybe in specific cases they do for these steps occurring, don't drastically fall off with time, but either increase or are fairly constant. But those are all additional complications. We're talking about here, and like you do in science, in all areas of science, you often start off with intuitive toy models to get yourself going. Then you say, well, it looks like we can get this result, and then you make it more complex. And there's additional complexities you've mentioned with considerations of adaptability and stuff. So it gets a very complex sort of situation. But hopefully this would pave the way to what you would have to actually look at to see whether the argument's going to work in the most very sophisticated models. Does that help answer your question?